In this section, we're actually going to get into your textbook. We're in Chapter 1, Section 1, and in here we're going to rethink our numeric representations in a manner that will support automation or support computation. In other words, how can we store numbers that will be most easily applied to a computer system? The answer is using binary numbers. We've already seen that before, but let's go back over it again. If we have an array of zeros and ones, we can interpret that as a binary number by using each number as representing a power of 2. So you can see the example here that that binary number would be 41 decimal. What we haven't seen so far is taking the same approach in representing fractions. We'll add what we call a binary point. It's analogous to a decimal point in the decimal system. And every binary value that's beyond the decimal point will become a fractional power of 2. So the first one is 2 to the minus first. There is no 2 to the minus second term because there's a 0 there. The third term, 1, means 10 to the minus third, and so forth. And that's how we will represent the rational components, really the proper fraction that is assigned to the whole number on the other side of the binary point. Remember, there's only 2 digits that exist, 0, 1. And all arithmetic that we'll do on a computer will be done in binary according to some scheme that we're about ready to entertain. This matches the digital nature of computers, which is why we're doing it in the first place. So let's take a look at some of the different representations of groupings of these binary numbers that we're going to use. The smallest of these three is called the bit. It will either take on the value 0 or 1. The next grouping is called a byte. In today's world, that is 8 bits. The byte can handle up to 256 values, in other words, 2 to the 8th power combinations. In modern computing, we usually use 4 or 8 bytes to form a word. There's also a floating point representation that we will use later. We'll either use the term single precision to mean that 4 bytes are used, or double precision to mean 64 bits are used. Most modern computers today will use the 8-byte approach. It's called 64-bit arithmetic. You've probably heard of that before. So let's take a look at an integer representation. There's more than one, but we're going to start with the simple ones. And the simplest form of an integer is called an unsigned integer. It's really the easiest to find because it's laid out just like we lay out binary numbers. And again, it's usually 1, 2, or 4 bytes. We'll be using a 4-byte example in the points that are following. They directly use the binary representation. And if you laid out a 4-byte integer, or I could say a 32-bit integer, and filled it up with ones, that would be the biggest possible value you could create, and it would look like that. There we have our 4 bytes indicated in terms each having 8 bits, and that number, which is the largest possible 4-byte integer that you could store, is 2 to the 32nd power minus 1. If you stick that into Excel or some other calculator and just run out that calculation that you see there, then that is going to be a number exceeding 4 billion. And that's as big as you're going to get on a 4-byte integer. Pretty simple though. It starts with 0. That's the littlest value you can have. You got zeros everywhere. And as you increment ones from the right side, the number keeps getting bigger until you fill the whole thing up with ones. Now, it won't take long before you're unsatisfied with the absence of negative numbers. You've got 0 out of that representation, and you've got a lot of positive whole numbers, but no negative numbers. So you might want to have a mechanism that would allow for a sign. Well, if we have to live with 4 bytes, as in this example, then I've got to use one of those up to tell me what the sign of that that string of ones actually is. So we're going to go to the leftmost bit, the one that probably is used the least, and we're going to dedicate it to play the role of a sign. And if that number is a 1, then we will interpret the rest of these 31 bits as being a negative number. And if that leading bit is a 0, then we will interpret the rest of those leading bits as a positive number. So that's what we're doing. 0 is positive, 1 is negative, and we call this the sign and magnitude method for integer or signed integer representations. Let's just take another look at it. If I just highlight the leftmost sign bit now as a 1, and I only allow the remaining bits to determine the value, well, I've actually lost a lot of numbers. You know, I mean, this number 2 billion and something is about half of the original number I got when I didn't mess around with the sign bits. But on the other hand, I am allowed to have both positive and negative numbers. So the 1 is going to produce a negative number, and the 0 is going to produce a positive number, and the range is nicely balanced. So let's get through a little more terminology. We have something called absolute error. That sounds depressing because it must mean that our calculations won't always come out perfect, and of course we've already talked about that is the case. So an absolute error is going to be the true result, which you never get to know, or generally don't ever get to know, minus our calculated value, which I'm calling estimate. And we take the absolute value of it because we don't want to deal with negative values on error. We also have a term called relative error, which is just taking that absolute error and dividing by the true answer. We're going to have a little problem with that if we don't know what the true answer is, but we'll come back to that issue. We'll also have something called accuracy or precision, and that will be the number of decimal digits that we can rely on. So let's talk about a little bit more pseudocode. We saw this before where we took a polynomial and we did this code. This was done last time where we wrote this little loop to evaluate some value of a polynomial. Well, first we can note that we can predict how many computations are going to happen. But if we look at this a little harder, I think we're a bit concerned about this exponentiation that's going on here. Now, honestly, that concern is probably something we would have been really concerned about 50 years ago before we had very modern coprocessors that do math fast. But really, this is kind of a waste. If I'm taking a number to a power, I'm doing a lot more work than if I just do a simple multiplication. And if I'm really dumb, maybe I do this power by just multiplying x by itself a whole bunch of times. And in fact, that logic is what leads to this formula here of the multiplication count. This is a somewhat inefficient code. It's order of n squared if I were doing that kind of silly thing of doing exponentiation the old way. And that's not often good. I mean, if I can do this in a linear manner, in other words, if I can make this order of n, where n is the size of the polynomial, I'll do better than if it's order of n squared. Well, we can do better than that. Let's try it in this case. Let's go back to our polynomial and just look at it different. Now, it's not going to look nicer mathematically, but it's going to look nicer to the computer. And that's how I want to reorder the computation. Now, I call this the onion peeling method. It's kind of like a reverse onion peeling where every one of these parentheses represents an onion peel, except I'm going to start at the middle of the onion and take the rightmost coefficient and multiply that by x, not x to the n, but just by x. And then I'm going to back up and take the coefficient before it, a sub n minus 1, and just add it to it. Then I will take that sum, or that linear combination, and multiply it by x again, and then add yet the other coefficient that's before it. And continue this process of multiplying by x and adding a coefficient going from right to left until I get all the way down to the bottom. And if we did this for just n equals 6, then here's what our polynomial would look like. And if I rewrote that polynomial using the same parenthetical or nested parenthetical approach, then it would look like this. I'll start from the end and I'll work backwards. but you have an opportunity to have a much faster code. So let's look at the P code associated with that. We'll lay out our integers like we did before, our real values of P and X. So P is going to be the result. We still have to build this array, and of course we're really going to need to put numbers in that. We'll not worry about that right now. But instead of starting off with a of 0, I'm starting from the right. I'm going to load up my polynomial with just the rightmost coefficient. Then I start my loop, but I'm going to run backwards. All I have to do is this very simple operation. Take whatever was in P, which starts off as the last coefficient, multiply by X, and add the previous value. Notice I only have one multiplication and one addition. And so my algorithm becomes order of n. I've got 2 computations, and I do it n times, so there's 2n computations going here, and that is a linear function. So we have greatly improved my code. Well, here's the code that would go with it. This is the actual MATLAB code that would work. And if you compare those two algorithms, what I call the onion peeling algorithm and the straight one, and if you plot what we call flops, floating point operations is what that stands for, then the old algorithm takes off in a quadratic fashion in terms of the size of the polynomial. But this yellow line represents the computations for the second algorithm. They're producing the same value, but the second algorithm is way more efficient. That's going to be a theme in this class. Efficiency is going to be a big deal. Saving memory, saving computation time is going to all be an essential part of the course. So in closing this section, let's look at some problems I'd like you to do, and then we're going to work problem 10 in your homework. Now let me give you a warning here. Your textbook has 2 sections of homework for every single section. The first section is what I call ordinary problems. They just call them problems. I'm trying to give it a name. I call it ordinary problems. And then they have a second section which are computing or computational problems. I will tell you which one you're going into by saying ordinary or computing. And this is just problem 10. It's not a computing section. So we're going to call this thing ordinary problem or ordinary problems 1.1. You'll need some values. You'll need to know what A and B are. And I want you to use these A and B values on that particular problem. There's also a second problem I want you to work, and that is problem 11a. Write pseudocode to do this polynomial. It's similar to the other, but not quite the same. So take a look and see what differences there are. Again, don't turn in your pseudocode to me on this. Just do it, and then turn that into MATLAB code, and you will send that in to me. You'll need parameters, and you'll need to know what n is, and you need to know what x is, so I've given them to you. If you'd like some extra credit for another 10 points, do problem 11a. So what I'm asking you to do with this extra credit point is to redo problem 11a analytically, in other words, on paper, and come up with a formula for this expression, okay, this polynomial. In other words, I don't want it to be a sum, I want it to be a polynomial in terms of n. And that's a little bit tricky, so you're going to have to take a look at it. I do have some hints for you I will send out, but the hint is viewing it as a geometric series and then monkey with it a bit, and you will need to differentiate it to make that formula work. And so that wraps up section 1.1. Good luck on that. We'll see you next time.